Hello everyone, and welcome back. Today we're going to continue our exploration of solving equations associated to some specific types of relations, in particular systems of equations. We're going to be considering both the linear and the nonlinear case for systems of equations, but mainly focused on the 2 by 2 case, and then we'll go into solving inequality systems and also a quick demonstration of the kinds of applications that you can actually use for these types of problems. So let's start off by giving a basic example of a problem that you would typically see in a systems of equations type of problem. So let's assume you were asked to solve the system 3x plus 2y is equal to 5 and minus 2x plus 5y is equal to minus 3. So if you don't know exactly what a systems of equation is, think of it this way. So if you just focus on the first equation here, you would obviously know that this is a linear equation in both x and y. So you can think, okay, well, what values of x and y satisfy this particular relation? And you're like, oh, well, there would be infinitely many of them. But can you also find a point x comma y that satisfies both the first and the second relation, which is also a linear relation? If you can, then that is a solution to this, what we call system of linear equations. So if you think about what's going on here in terms of the geometric nature of this systems of equation, what we have here is two lines in 2D space. Right? So if you have two linear equations in 2D space, in particular x and y, no z, no w, no t, no anything like that, then you have a couple cases that might arise in the solutions of this type of system. So one case that you could encounter is where you have one line here and one line here. So is there any point x comma y for which these two lines intersect? Obviously no. So in this particular case where you would have two parallel linear relations, there would be no solution to that associated system. So you could also have, for example, a linear relation here and a linear relation here, right? And obviously there's one particular point for which this crosses, so that's x and y. So there would be one solution associated to that particular systems of linear equations. And you could also have, for example, this line here and this line here directly on top of it. So obviously there would be infinitely many points that lie on that line that would satisfy that systems of equations. So it would be infinitely many solutions. And those are the only three cases that you would get with two lines in 2D space, right? And keep in mind, infinitely many solutions is not the same as all real solutions, because there's obviously a point, for example, here that would not be a system of that systems of linear equations. Right? So let's go through a few variations of solution strategies that you can actually use for 2 by 2 systems of linear equations. So 2 by 2 systems of linear equations, and you can use some of these strategies for other equations, 3 by 3 systems of linear equations, and also nonlinear equations as well, right? Linear equations. Okay, so the first method, so method 1, is probably the simplest in terms of how to understand it. This is called substitution. Substitution. So let me illustrate how substitution goes. So keep in mind we have two equations, 3x plus 2y is equal to 5, and minus 2x plus 5y is equal to minus 3. So what we're going to do here is we're going to take one of these equations and solve for one of their variables. For example, we can choose the first equation, and for example, we can solve for y. And you could also solve for x. It really depends on your preference, but in some sense you will be able to find which is going to be easier for the solution strategy eventually once you do a few examples. So let's take the first equation and solve for y. So once we do solve for y in that particular equation, we're going to have y is equal to 5 halves minus 3 halves x, or 5 minus 3x, all divided by 2. So that's what we get there. Once we get this particular relation, what we're going to do is we're going to take this and substitute it in for y in the second equation. So once we have that, we're going to have minus 2x plus 5 times the quantity, 5 divided by 2 minus 3 divided by 2, x, and that's going to be equal to minus 3. And notice what we have here. That is just a simple linear equation with one unknown variable, x. Okay, so let's clean this up a bit, and let's actually get rid of these fractions in the bottom. So let's multiply both sides of this equation by 2. So once we do that, we're going to have minus 4x plus 5 times 5 minus 3x is equal to minus 6. In case you don't know what's sort of going on there, this 2 distributes there, this 2 distributes there, and then we distribute it into those interior two fractions, and that 2 is obviously multiplied by minus 3. So now we're just going to distribute that 5 in, so we're going to have minus 4x plus 25 minus 15x is equal to minus 6. And what we have going on here is we have minus 19x is equal to minus 31. So we're going to have that x is equal to 1931, and that's going to be a positive quantity. And of course that should be flipped upside down, 31 divided by 19. Okay, so once you have your x value, now we can find our y by substituting that back into our y relation. So keep in mind y is equal to 5 halves minus 3 halves of x, and x is 31/19. So I'm just going to multiply that by 19 to get that common denominator. So we're going to have that y is equal to 19 times 5 minus 3 times 31, all divided by 2 times 19, and that is going to be equal to 2 divided by 38, which does reduce to 119. So once you have x and once you have y, that means you have found the solution to the system. So that means we have one solution, and the solution is the point xy is equal to 31/19 and 1/19. So obviously we can see with this first method, it definitely does work. You have to be comfortable with fractions, generally speaking, but it definitely does give us the solution to that equation. And you can substitute this point into the first and second equation and verify that it actually does work for both. The next couple of methods are actually more preferred, especially when you're dealing with 3x3 or higher dimensional systems of linear and nonlinear equations, and that is Gaussian elimination plus back substitution, and another method which is referred to Gauss-Jordan elimination. So let's start off with what Gauss-Jordan elimination followed with back substitution actually looks like. So let's look at the same exact systems of equations that we had before. So keep in mind we had 3x plus 2y is equal to 5, with minus 2x plus 5y both being equal to minus 3. So what we aim to do here is try to rewrite these relations in equivalent representations such that the coefficients of either x or y, and it's up to your preference of which you would focus on, are the same exact value. So obviously 3 and minus 2 are not the same number, but if I multiply 3 by 2 and negative 2 by 3, then both of them are going to be 6 and minus 6. So what I'm going to do is I'm going to focus on this term and make them the same. So I'm going to multiply this equation by 2 and this equation by 3, and in some sense you can see they're practically the opposite switched numbers. So once I do that, I'm going to get an equivalent systems of linear equations, in particular 6x plus 4y is equal to 10, and minus 6x plus 15y is equal to minus 9. Right? So once I have these equations, which is the same exact equations, just now reduced, now I'm going to add these equations, And why am I adding them? Because 6x plus negative 6x will be 0x. So these two will eliminate. Now, if it's 6x and positive 6x in both, then you would be subtracting those equations so they cancel, right? But in this case, they're opposite signs, so we're going to be adding. And when we add, we're going to have 19y is equal to 1, giving us y is equal to 1 over 19, right? So once we have y is equal to 1 over 19, then we can go back to our first equation, which was 3x plus 2y, and substitute that value of y in and solve for our value of x. So this is our Gaussian elimination. And now we're going to do our back substitution. Right? So Gaussian elimination followed by back substitution. So Gaussian elimination is what we're going on here. We're eliminating the variable by, making the coefficients the same. And once we find one value, we use back substitution. So once we do that, we're going to have 3x is equal to 5 minus 2 over 19, and then we can divide both sides by 3, and that's going to give us x is equal to 5 divided by 3 minus 2 over 19 times 3, and we can multiply that by 19, and then we're going to have, in the end, 31 over 19 as our x value, which is the same exact solution value that we had in the previous example solution. So again, this last part can be a little bit messy, but the very first part is actually pretty nice, which motivates how method 3 goes. Because obviously, if you don't really like fractions, this back substitution can get quite annoying. So method 3 seeks to avoid any substitution, so in particular, getting rid of those fraction things that might arise. And this is called Gauss-Jordan elimination. So it's going to start off with Gaussian elimination to eliminate one variable, and then it's going to use another elimination strategy to eliminate the other variable. So let's sort of see how that's going to go. So we're going to have 3x plus 2y is equal to 5, and minus 2x plus 5y is equal to minus 3. So, just like before, what we're going to do is we're going to multiply this by 2 and this by 3, and that's going to give us an equivalent systems of equations, in particular 6x plus 4y is equal to 10, and minus 6x plus 15y is equal to minus 9. Once I have that, then I can add these equations together, and that's going to have 19y is equal to 1. Now, I'm not going to divide by 19 because I don't want to work with my fractions quite yet. So what I'm going to do is I'm going to rewrite my equations, in particular this one and this one, into the same. So I'm going to have 3x plus 2y is equal to 5, and 19y is equal to 1. Now I'm going to focus on eliminating my y term, and I can easily do that by multiplying this by 19 and this one by 2. So once I do that, 19 times 3 is going to give us 57. So we're going to have 57x plus 19 times 2, that's going to give us 38. Y is equal to 19 times 5, which is going to be equal to 95. And then we're going to have 19 times 2, which is going to be equal to 38y. And that's going to be equal to 2 times 1, which is going to be equal to 2. Once I have that, then I can subtract these equations to eliminate those. And then we're going to have, so 57 minus 0x is just going to be equal to 57x, and that's going to be equal to 95 minus 2, which is 93. So we have 57x equals 93, and we can go back to our original version of equation 2, which is 19x is equal to 1. Now that we have this type of equation, and of course that last equation should be y, now we can divide by those linear coefficients which are non-zero, and that's going to give us x is equal to 93 over 57, and y is equal to 1 over 19, and this first value, of course, will reduce to 31 over 19, which is the same exact solutions that we had before. Right? Now what I want to do is show you another variation of elimination that is especially fast for 2x2 systems, right? So method 4 is primarily focused on 2x2, and this is referred to as double elimination, or double Gaussian elimination. So what I'm going to do is I'm going to do 3x plus 2y is equal to 5, and minus 2x plus 5y is equal to minus 3. And I'm going to write the same exact system over here. So 3x plus 2y is equal to 5, and minus 2x plus 5y is equal to minus 3. So on one of these systems, I'm going to focus on eliminating x, and on the other, I'm going to focus on eliminating y. So for example, if I want to focus on eliminating x on the first, again, I'm going to multiply that by 2 and that by 3. And over here, if I'm going to focus on y, I'm going to multiply this by 5 and that by 2. So once I have that, that's going to give us 6x plus 4y is equal to 10, and minus 6x plus 15y is equal to minus 9. And then I'm going to add. Over here, we're going to have 15x plus 10y is equal to 25, and minus 4x plus 10y is equal to minus 6, right? And obviously for this, I'm going to be subtracting. So once I have that, I'm going to have 4 plus 15 is going to be 19y, and 10 minus 9 is going to be equal to 1. So here we have that y is equal to 1 over 19. Over here on the right, I'm going to have 15 minus negative 4, that's going to be equal to 19x, 10 minus 10 will be equal to 0, and 25 minus negative 6 is going to be equal to 31, giving us x is equal to 31 over 19, right? So therefore we have that our solution, xy, is going to be equal to 31 over 19, comma 1 over 19, which is our solution as we already know. Right, so I think double elimination is probably one of the more faster ways for the general systems of equations, especially if you want to solve this by hand via, for fast-paced testings like the SAT or any other testing methods as well. The next method probably would only be viewed as a better method if you happen to not know any algebraical methods to solve this systems of equations, and this is the method of graphing. Of course, this is not very useful, especially if your graphing by hand is not exact, but it is extremely powerful if you do have a graphing calculator or graphing software on a computer that can graph it for you up to whatever degree of accuracy for which you desire. At least for this particular systems of equations that we're working with, it is the systems of linear equations, and graphing linear relations isn't that difficult. So what I'm going to do is I'm going to rewrite each of these equations in slope-intercept form, so y equals mx plus b. So the first relation will be transformed into y is equal to negative 3 halves x plus 5 over 2, and over here we're going to have y is equal to 2/5 x minus 3/5, and this is going to be my systems of equations in slope-intercept form. So I'm going to call this, for example, line 1 and line 2. So we see line 1 has a slope of negative 3 halves, y-intercept of 5 halves, and line 2 has a slope of 2/5 and a y-intercept of minus 3/5. Right? So at least in terms of accuracy, we can plot the y-intercepts with reasonable accuracy. So for example, if this is 1, 2, 3, and 4, and then over here we have 1, 2, 3, and 4, 1, 2, 3, and 4, 1, 2, 3, and 4. Spacing is probably not exact, but generally speaking, it's not too bad, I guess. So what do we have here? So 5 halves, as we know, is 2.5. So that's going to be located somewhere about there. So that's going to be for line 1. And this is negative 3/5, which we know is negative 0.6, which is somewhere about here. Right? And if we find the x-intercepts for each of these lines, so if we want to find the x-intercepts, we're going to set y equal to 0, and that's going to give us 3x is equal to 5, and minus 2x is equal to minus 3, which is going to give us x is equal to 5/3 and x is equal to 3/2, right? So that's going to be approximately equal to 1.6 repeating and 1.5. So the x-intercepts for these are actually pretty close to each other. So the first point of 1.6, let's say it's going to be slightly over here. And the pink x-intercept is going to be slightly before it, right? So let's see if we can sketch these lines out. All right, so there is line 2. And then here we have line 1, right? So if our sketches are exact, and I don't think it's super bad, we do have one solution located there for which the x and y coordinates are both positive. Obviously in this particular case it's not very clear what this value is, but one can show via algebraic methods as we've already done in a few ways. This is going to be 31/19 and 1/19. So the 1/19 pretty much makes a lot of sense because it's barely above the x-axis, so it's really close to 0. And 31/19 is not quite equal to 2, so I guess this should be shifted up a little bit more, but you know, I can always lie with my y-intercepts and shift that down and lie, I guess, but you know, in some sense it's gets the general point across, right? But as I said before, you probably wouldn't be using graphical methods for solving systems unless it was a pedagogical example of a linear system or a very cute nonlinear system, or you have software and graphical calculators that can give you a bit more accuracy on your graphing. So what I want to do now is actually switch our attention from systems of linear equations and focus on systems of inequalities. And to keep things interesting, I'm not going to consider a system of linear inequalities, I'm going to consider a system of nonlinear inequalities, right? So, in particular, let's suppose we have x squared plus y squared is equal to 1, and y minus x is equal to 0. So this is not a system of inequalities, this is going to be a system of equations, but I'm going to switch this into inequality form in just a moment. So what is this relation? If you know, you might want to, say it out loud to yourself, but this is going to be a circle centered at x, y is equal to 0, 0, with radius equaling 1, right? Some people refer to this equation as the relation for the unit circle. And we already know that this is just a line, right? So if I were to graph this particular systems of inequalities, let's assume that this is relation 1 and this is relation 2. So if this is 1, 1 minus 1, 1, then relation 1 is going to be this not so pretty circle. So that's relation 1. And then our line, y minus x equals 0, which is the same as y is equal to x, is going to be this line. So this is relation 2, i.e. y is equal to x. So if you can graph these two relations in systems of equations form, we can actually use this to solve systems of inequalities as long as our graphs are relatively nice. So now I'm going to change this to x squared plus y squared is less than 1, and y minus x is greater than or equal to 0. And the equal sign on one of them or both of them or neither of them does matter. So x squared plus y squared equals 1 is a unit circle, as we already know. So what is x squared plus y squared less than 1 going to be? So one can show that that is actually the interior of the unit circle. So let's just draw our boundary here, because keep in mind it can't be equal to 1, so it's not going to include all of these points. It's not quite a pretty circle, but pretend it is. So less than 1 is going to be all points inside this circle, right? So this is inequality 1 or region 1, let's say. And y minus x is equal to 0 is going to be this line. Keep in mind it is a equal sign here, so it is a solid line. And it's going to be above that line because its y is greater than or equal to x, right? So all values in this particular region, I'm going to call it region 2, are all points in this pink shaded region, including that line, right? So where are all of the solutions to this system of inequalities? It's where these two regions overlap, right? which is going to be this area here, right? So if I clean this up a bit and only shade what I'm interested in analyzing, so I'm going to have my unit circle, which is non-inclusive. I'm going to have my y is equal to x line, open circles at the tails because it has to be satisfying both of them. Obviously our line is going to go outwards. And the solution for this area is going to be the interior of this circle and including this line segment in the middle, not including those endpoints. Right? So there's infinitely many solutions. Any point in that region will work. For example, some solutions, and you can find infinitely many of them actually, would be, for example, negative 0.5, negative 0.1, negative 0.9, negative 0.4 will work. Negative 0.5, 0.85 will work. Negative 0.65, 0.74 will work. So all of these points are sort of scattered in this region somewhere, and you should be able to give me several points that are not actual systems to this system of inequality, right? But that's pretty much how you can solve systems of inequalities via graphical methods. And you can plug in several points into both and see which one works if you're interested in particular solutions to that system. Because generally speaking, there will be infinitely many points that will satisfy this particular system. Now that we know how to solve a variety of systems of equations, both linear and nonlinear, and also how to solve a system of linear inequality or nonlinear inequality, now I just want to illustrate just a basic example of some of the types of things that you can solve with these types of structures. Now, of course, there are infinitely many different types of applications that you can solve with systems, but these are usually more explored in, say, a linear algebra or optimization methods course. So I just want to just do this basic example just to get your feet wet in terms of what we're actually looking at here. So let's suppose that you have $5,000 and you're to invest this into two separate accounts, A and B, where A has a simple interest rate of 5% and B has a simple interest rate of 10%. So over time, let's assume you invest 1,000 in A and 4,000 in B. Over time, it's going to accumulate interest at some particular speed. In particular, B is going to accumulate interest at a faster rate. That balance is going to increase over time, provided that you do not make any withdrawals or have any penalties or fees, and so on. So after 1 year, so key here, 1 year, if the total interest gain across both of the accounts was $400, how much was invested into each account on day one? Okay, so let's sort of get an idea of what we're looking at here. So we're going to have some amount, I'm going to call it X, and that's going to be deposited into A, which has a simple interest rate of 5%, and Y is going to be deposited on day one into account B, and its interest rate is 10%. So notice that we know that the total of X and Y is $5,000, so we know that X plus Y is going to be 5,000. We just don't know how much is allocated to A and how much is allocated to B, but we do know the total of those two allocations, right? So this is the first equation that we have. Next is going to be associated to these interest rates. So the simple interest rate formula is going to be I is equal to PRT, where P stands for the principal amount that you invest, R is that simple interest rate, and T is the amount of time, and in our case, T is equal to 1 year, right? And keep in mind, if you're changing units like monthly or daily interest rates, make sure that T and R are in the same unit, right? So we know that the interest accumulated in balance A is going to be equal to something, which we don't know, and the interest rate in B after 1 year is going to be equal to something, which we don't know. But after 1 year, we know that the total of these two interests came out to $400, right? So we don't know the amount that was invested into each of these accounts because that's what X and Y are equal to, right? But we know the rates are 5%, which is 0.05, and 10%, which is 0.10, right? So we can use this equation in terms of this X and Y and write that out. So that's going to give us 0.05 of x times 1 plus 0.10 times y times 1, since it's 1 year, and that's going to be equal to $400. All right? Now, you might not like these decimals, so you can multiply both sides of this equation by 100, and you can say that this is just going to be equal to 5x plus 10y is equal to 40000. Right? So that's one equation, and we also know that x plus y is equal to 5,000. So now we have a system of two linear equations with two unknown variables, so we should be able to know how to solve this, right? So let's start off with Gaussian elimination. So I'm going to be focusing on this y, so let's assume I just multiplied that by 5 and that by 1. So once I have that, I'm going to have 5x plus 10y is equal to 40,000, and then 5x plus 5y is equal to 25,000, and then I'm going to subtract these equations. So I'm going to have 5y is equal to 15,000, and then I can solve this equation for y, so we're going to have y is equal to $3,000 that was invested into that account. Then I can substitute this value of y into this equation and solve, and then I'm going to get that x is trivially equal to $2,000. So quite nice numbers, right? So the amount that was invested into account A, so the principal balance of A, was equal to $2,000, and the principal balance of B was equal to $3,000, and that's what our problem sought out to solve. Right? So that's just a basic example of things you can solve with systems of linear equations, and one can also do it for inequalities. Hope you enjoyed this video, and I'll see you in the next one. Take care.